Hi everyone. So today we'll be focusing on a problem that includes needle nose pliers, and this is for the class of Applied Mechanics. So to begin, I'll explain a little bit about these needle nose pliers that we used. So the objective of the problem is to find the magnitude of the forces applied onto a small screw that would be wedged in between the two members of the pliers and on the pin in the middle of a set of pliers using statics. We will first disassemble the set of pliers into the two individual members to be able to visually analyze the forces and the moment that's applied to each member and also the pin. The pliers that we used are made with alloy steel, and the red bindings on each of the handles are made with rubber for the purpose to give the user an easier handle on the grip. So the actual problem that we will be trying to solve is a pair of needle nose pliers are used to grip a 1.5 centimeter diameter of a small screw. The user applies a force of 222 newtons onto each of the handles. Figure out the magnitude of the force R that is being exerted on the small screw. Then find the magnitude of the force reaction at the pin, represented by A, on the member represented by AB of the set of pliers. So you can see the two members are represented as B and C, so you could interchange AB or AC. So how do we approach this problem? Okay, we first, like I said, disassemble the pliers. So we created free body diagrams to help visualize the acting forces. This will ultimately help find the unknown magnitude exerted onto the screw, which is represented as R, and the force exerted by the pin at A in this situation. So on the left, we see the free body diagram of the pin, and on the right, we see the free body diagram of the member AB of the set of pliers. So in the free body diagram of the pin, the direction of the force in the X direction is pointing to the right, and the force in the Y direction is pointing upward. So how do we start this? Well, first, we take the moments about A. So the sum of the moments in A have to equal 0. In order to find the moments in A, we have to include R, the 3.8 centimeters, the forces applied, and the length of the member. So the two parts of the member, which would be the length of the member and the forces applied, would be subtracted from the parts of the pin and the screw, which would be the length of the middle of the pin to the screw and the R force. So on the right, you see our calculations. So you multiply R and 3.8 centimeters, and you multiply 222 newtons and 13 centimeters. You end up getting 3.8 centimeters times R will equal 2,886 newtons times centimeters. Then R would ultimately equal 759.47 newtons. That is our R value, and we will continue to use it throughout the rest of the problem. Second, we have to resolve the forces along the horizontal direction. That is AX. So the sum of the forces along the X direction have to equal 0. We include in this Fx the A of X, which is the reaction force in the horizontal direction, sine of the angle, which is 30 degrees, and R as well. So they all equal 0. R, we substitute what we found before, which is 759.47 newtons, and we multiply that by the sine of 30. We end up getting negative 379.735 newtons as our A sub x value. Then we do the same thing only along the Y, the vertical direction. So the sum of the forces in the Y direction have to equal 0 as well. In our Y direction, we have to include A sub Y, same as before, R and the angle. But this time we have to also include the force applied because it is also in the vertical direction. So you see that we do R cosine 30. So we substitute our value of R again, and we find the cosine value of 30. And then we have to subtract 229 from that value as well. And then we move everything to the other side to get a sub y, and we have a value of 879.72 newtons. Then we want to calculate the direction of the forces. So the direction of the forces is calculated by taking the inverse tangent of a sub y divided by a sub x. And this would be the resultant force. So the resultant between the two forces is shown here. And we just substitute the values that we found before, 879.72 newtons and 379.74 newtons. In this case, it is not necessarily negative, and we don't want a negative angle. So we end up getting 66.7 degrees, and that is this angle right here. Then we have to calculate the magnitude of the resultant force at A. So by doing this, it is equal to the length of A, which, as we know from calculus and also from statics concepts, the length of a vector is just the square root of the two components squared. So we substitute our A sub x value and our A sub y value, and then we use the equation plug and chug. We find a value of 958.18 newtons for the magnitude of the reaction at A. And lastly, I include some CAD 3D drawings for the purpose of building a model that represents each of the parts of the device in more depth. So in the first one, you can see that the model is completely transparent and every individual part of the pliers can be seen. All the little lines are all the individual parts. In the model of the set of the pliers that is not transparent and the model of the head of the pliers that is also not transparent, they just serve the purpose of illustrating the devices in specific detail for engineers like you and me to fully grasp what members they're working with in order to complete the task efficiently and accurately. So these drawings ultimately help analyze the set of pliers before going ahead and solving the problem at hand.